talking about syntax and semantics another look. Please.
Thank you. Okay, I have a technical result which I will almost certainly not show you any details of. The purpose of my talk is to go through my motivation for being interested to prove such a result. So I have 6 slides on the main part of my talk, which might take me the whole half hour, 25 minutes. But if it's much quicker, I have some further slides which will go a little bit into some of the details and give definitions, but I'm not necessarily going to want to go into those technical details. Okay, so I've introduced this notion of generalized type setup. It's my preferred notion for the abstract syntax of dependent type theories. So by a type theory, I will always mean a dependent type theory, and I will think of a dependent type theory, a type theory, as the syntax being, the concrete syntax being represented in what by now is a fairly standard way of representing dependent type theories. The notion of an FCC, a full comprehension category, is a particular category theoretic notion. It involves a particular kind of fibration. Now, I'm not an expert on category theory or fibrations, and for that reason I had a hard time proving this theorem. If there are any category theorists in the audience, which I suspect there may not be, but if there were, they might be able to help me to find a better way of proving this theorem. Okay, so an FCC is a particular kind of approach to the semantics of dependent type theories, and in the literature over a number of years, many category theorists have formulated many notions of how to do semantics for dependent type theories. And the notion of an FCC is just one among them, which is perhaps the most general approach to giving semantics. And my notion of GTS, so I get this theorem for comprehension categories, but not for the other notions. So what's going on? So there's a distinction between the traditional approach to syntax and semantics and the way category theorists usually treat syntax and semantics. So the traditional way, there's an idea of concrete syntax, whereas the category theorists prefer a rather abstract notion of syntax, where say an algebraic theory is some particular kind of category, and then an algebra, a model of the algebraic theory, is then viewed as a particular kind of functor defined on that category. And because of that way of thinking, category theorists prefer to abstract away from the variables, both free and bound in abstract syntax. I'm perfectly happy to abstract away from bound variables, thinking of, say, well-formed formulae of logic up to alpha convertibility, but I don't like the idea of doing away with the free variables, abstracting away from free variables. So I'm taking a rather traditional approach, but I still like the category theoretic approach to many things, although I'm not a category theorist. So the motivation, the motivation I want to present here was not the original motivation why I came to this uh, uh, the topic of this talk, but the motivation I want to present here is to do with homotopy type theory. So I want to say a few words about that, but it'll be very brief. So it's intended to be a type theory. So homotopy type theory is a type theory obtained from one of the standard type theories, that intentional type theory such as Per-Martin-Löf's, or perhaps the Koch type theory, the type theory implemented in the Koch system, by adding an axiom which is only a few years old, introduced by Voevodsky, the univalence axiom. And there are possibly other additional rules one might want to add in homotopy type theory. More recently, about a year and a half old now, is the idea of something called higher dimensional inductive types, which seem to be playing a very important and useful role in homotopy type theory. So the ideas of homotopy type theory involve an amalgam of ideas, first of all from type theory, because it is a type theory, and higher dimensional category theory, and particularly higher dimensional groupoid theory, and homotopy theory itself. So the issue for my talk is how to do homotopy type theory mathematics. I think of HOT as an alternative to doing classical mathematics or doing constructive mathematics. I think it's on that level. So I'm going to show you three possible answers to this question, how to do homotopy mathematics. First approach, develop machine-checked formalization in Koch or Agda. Koch or Agda are nice for our purposes because they implement an intentional type theory. So one can choose to see what happens if we add, say, the univalence axiom and what one can prove from that, and possibly also with if one can implement the rules for higher dimensional inductive types in Koch or Agda, then that would be very nice. The second approach is to develop in a model of homotopy type theory using classical meta theory. And we're all used to doing classical mathematics, so that can be an easy thing to do if you don't like using a more easy thing to do if you're sufficiently familiar with the category theoretic models of type theory to take the second approach. The third approach is to develop mathematics informally in homotopy type theory. Okay, so at present, most of the people working in homotopy type theory are actually following the first approach. They are generally not used very much to doing mathematics in type theory, and doing the mathematics in Koch is very convenient because it checks whether your proof has been done correctly. So this is the main approach being taken. I favor the third approach, which I think is equally important, if not more so. So I think mathematics ought to be presented informally. One shouldn't be an expert in using some computer system because they are not sufficiently good at present for everyday use by mathematicians. So mathematics ought to be presented informally. Unfortunately, informal mathematics has evolved on the whole in a set theoretical style, and all sorts of conventions are implicitly introduced into doing informal mathematics in the set theoretical extensional style that we're all used to. Maybe category theorists advocate a more category theoretic approach than the set theoretical one. But nevertheless, there is no tradition yet of doing mathematics in type theory informally. So it is necessary to develop such a tradition. I should say that in the 1970s I felt this need to develop to be able to do mathematics informally in type theory for some reason I won't go into. I found it hard work to try and develop a good style, but I think it's very important to do so. And that's one of the reasons I switched to looking at constructive set theory to do constructive mathematics rather than type theory. Although in some sense, from a philosophical point of view, for constructive mathematics, type theory is more explicitly constructive. Okay, so that's the motivation. I want to say a few words about type theory. So I'm not sure many of you will be that familiar. So the usual concrete syntax of type theory, there will first of all be something one might call raw syntax, where you just generate some expressions and put them in different syntactic categories in a fairly straightforward, familiar way, using an alphabet of symbols that you want to use. And then you have rules of inference for deriving things called judgments. And each judgment has the form indicated there. It consists on the left-hand side of a context of variable declarations. And on the right-hand side, the body of the judgment will have one of a limited number of forms, and the usual standard approach is to have these four kinds of form. Saying that something is a type, saying that two types are equal, A and A prime are equal, saying that little a is a term of type capital A, and saying that A and A prime are equal terms of type A. The equality here is called judgmental equality because in type theory there are other equalities around which have to be kept distinct. It's only in extensional type theory that there's some kind of identification of different kinds of equality. So we have this judgmental equality, which is also sometimes called definitional equality. There are some constraints. Each free variable of the type AI must be among the list x1 to xi minus 1. You may not be used to having types involving free variables, type expressions involving free variables, and that's the whole point of dependent type theory, is that type expressions can involve free variables. And the free variables in B must have been declared in the context. Among the forms of type, there are many forms of type. There are pi types, sigma types, etc. But among them is a particularly important type for homotopy type theory, identity types, which from the logical point of view are types expressing the usual mathematical notion of equality between objects of a type. And they have this formation rule. If we have two terms, A1 and A2 of a type A, we can form this identity type. And this is a clear way where types can depend on variables, because there may be free variables in A1 and A2, and then they will become free variables in the identity type. In homotopy type theory, in the topological model of type theory, identity types if A is the type of a space, topological space, then the identity type A1 identical to A2 turns out to be the type of a space of paths from the point A1 in the space for A and the point A2. So it turns out that the identity types play the role of corresponding to path spaces. So that's giving you a little bit of an idea of how type theory is linking up with homotopy theory. Logic in type theory is usually not primitive, but defined in terms of the type theory notions. In particular, each proposition is viewed as a type. As you saw with identity types, from the logical point of view, one might think of that as the proposition that A1 equals A2. But there are different treatments of logic in different approaches to type theory. In Martin-Löf type theory, propositions and types, on some way of thinking about Martin-Löf type theory, are simply identified. Every type is a proposition, every proposition is a type. And the logical operations are appropriate time-forming operations using the Curry-Howard correspondence, if you're familiar with that. In the Coq type theory, it's somewhat different, although it's not often realized that the Coq type theory does not use what I would call the propositions as types, which I think of as propositions equals types. Indeed, in the Coq type theory, every proposition is a type, but it's only the types in a particular type universe prop that are interpreted as propositions in the Coq type theory. The types in general are not. And finally, in homotopy type theory, at the moment I'm unclear how logic is best treated in homotopy type theory. But one approach is to treat propositions as things called homotopy level 1 types, i.e. types where each identity type on that type, A, has homotopy level 0. In the topological model, or a topological model, in that topological model using the category of simplicial sets, which is a particular category that homotopy theorists like to use, the homotopy level 0 types are simply the homotopy types of the contractible spaces. That's just a brief giving you some idea of some aspects of homotopy type theory. Let's go to syntax and semantics, the main point of my talk. There's a tension between the traditional approach to syntax and semantics and the categorical approaches. The traditional approach for syntax aims to be close to informal mathematical practice. At least that was one of the foundational original motivations for the traditional approach to syntax, while the categorical approach aims at good algebraic notions. The traditional approach keeps to a more concrete syntax, i.e., in my view, keeping free variables, or for example, as one aspect of being concrete, while the categorical approach aims usually at a much more abstract approach, often abstracting away both the bound and the free variables. You might ask, how is that possible? Well, if you remember the form of a judgment, it has a context listing the variable declarations, and then the body of the judgment can involve free variables, but only those that are free relative to that have been declared in the context. Now, if one thinks of the context as a binding operation, then it seems somewhat natural to think of even the free variables occurring in the body of the judgment as being bound by the context, and therefore thinking of them up to alpha convertibility. So one can see that it's not too unnatural to think of free variables as being bound. But it's unnatural from the point of view of someone doing informal mathematics who is used to having free variables around. So I don't like treating free variables up to alpha convertibility in this way if one is concerned with having a good way of treating syntax in connection with informal mathematical practice. Semantics, the traditional interpretation of concrete syntax, is given by recursion on the structure of the expressions which have been inductively generated, while a categorical approach would represent an abstract syntax as a certain kind of category, and an interpretation of it is presented as a suitable functor on that category. For example, for many-sorted universal algebra, an abstract algebraic theory, category theorists often would take to be simply any Cartesian category. And an algebra for that algebraic theory will just be a Cartesian functor on T into the Cartesian category, into a Cartesian category such as the category of sets. A Cartesian category is simply a category with explicit finite products. So I consider this a very abstract, elegant, mathematically elegant approach to universal algebra. But it doesn't correspond to mathematical practice when one wants to usually introduce, say, the algebraic theory of groups or any other such standard algebraic theory. Okay, so that's actually the end of my basic slides for this talk. Now, when should I stop? When did I start?
You stopped at 38 minutes.
Sorry?
At 38 minutes, so.
38. So I have another 8 minutes for talk and questions, right? So I'll try and just take well, maybe I can start with questions now. What would you like me to show next? Well, I'm asking the question to you.
The next slide.
Sorry?
The next slide.
The next slide actually involves my original motivation for doing this before I even heard of homotopy type theory and before it was even invented. So I showed you the usual, so my original problem, which led me to looking at generalized type setups, was the idea for a logic enrichment of a dependent type theory. Usually, type theorists take a particular way of treating logic, and in particular, the Coq system treats logic in a particular way, whereas I used to prefer the treatment of logic of Per-Martin-Löf, where you just identify propositions and types. Unfortunately, the Coq system has fixed on its way to treat logic, and therefore I felt unhappy with using the Coq system because it was awkward. In fact, homotopy type theory also doesn't like the Coq treatment of logic and prefers to use another treatment of logic. So there's a huge Coq library of machine-checked mathematics which homotopy type theorists cannot use because the logic that they use, that Coq people use, is so inbuilt into the library. Now this has always annoyed me about the Coq system, and I've wanted to try and persuade the Coq people to not focus on using that library, but taking a more flexible approach that one should be able to base the logic library on a general treatment of logic, which can then be instantiated in whatever logic is your favorite logic. So that's the idea of logic enrichment of a dependent type theory. You just add logic on top of the type theory. But I wanted to do this in a traditional way, keeping free variables. We're used to using logic with free variables, so it was necessary to have the type theory itself having free variables around. and so that led me to the idea of logic enrichment of a dependent type theory. I wanted a precise notion of syntax for dependent type theory, which was more abstract than the concrete syntax I've been talking about, as one usually uses, but nevertheless has free variables. So that was a motivation. So a generalized type setup is such a thing, and I have 3 or 4 minutes, well, 2 or 3 minutes left. There are lots of notions of abstract notions of category for dependent type theories, but they've all been introduced by category theorists focusing on semantics, really. So I've got 2 slides. I think I'd better stop there. It would take me longer. There are only 2 slides on generalized type setups, but I think I'd prefer to stop there.
Thank you. Questions?
So when you say you were trying to develop mathematics, kind of doing mathematics in a constructive way, and this was somewhat frustrating, you said before.
Doing it in dependent type theory was,
Yes, earlier on.
was frustrating, yeah.
Whereas now the vision is supposed to be that we're going to be able to do mathematics using homotopy type theory. I mean, how far will this work for kind of analytical kind of theories, like analysis, as opposed to algebraic theories?
Well, Voevodsky is working on developing everyday mathematics. I don't know if he's got to analysis yet, but he's certainly keen to do so. Yes, I don't know exactly.
It should be able to do.
There are lots of nowadays.
Analysis.
Yeah, there are lots of people working on homotopy type theory. Well, there are a considerable number, and they are developing. I don't know if other people besides Voevodsky are actually developing standard mathematics, but there is at least the main person, Voevodsky, is certainly doing so.
In what sense would you say does homotopy theory make it easier to develop it informally?
Could you say that
Would it
again?
make it easier? Would it be easier to do informal mathematics in homotopy type theory than in standard type theory?
And standard dependent type theory? No, it's the same issue. I don't see why. You may have a point there. The univalence axiom suggests possibly that may lead to simplifications. Yes. Yeah.
I'm thinking about it because I think intentional type theory is unsuitable for informal reasoning because one makes permanently mistakes because we think very extensionally. So it's working in an extensional framework is easier.
Yes,
So
homotopy type theory is intentional still in one sense, but a theorem proved using the univalence axiom is function extensionality. If 2 functions are extensionally equal, then they're actually equal, where equal means using the identity types. Yes, it may become easier there for that reason. But I haven't thought through, that remains to be investigated.
Thank you very much.